easy?
Oh, yes, I see my toilet.
I'm a student.
This is for, this is for.
Oh, faculty, I'm in San Nicolas.
I saw
You
it.
might have to join
I
every.
saw, it's okay, I saw somebody trying to give me some, and I was like.
Well, I know this looks for everybody.
Yeah.
Oh, you can throw it away. So
Okay.
I can tell you which one is mine.
I wrote your name on the ones.
Okay. So,
Okay.
sorry about that.
It's okay. Thank you.
Yeah, yeah, I would. It's like state depths. That's what I gotta be tough. We should go
The
first
first
test.
test.
I mean, I thought we should have. Oh, we don't. Gives it a little. Okay, I'll make sure. Yes. As long as it's good. Oh,
I'll do it myself. I think two other people in there just. I usually like to see something I stay up a little bit before. So I can really usually sit down and do stuff like that.
It's the time one.
Okay, let us get started. As soon as you're ready, please.
Look.
Please just a minute, don't hold it too long. Turn it on.
Look.
There it is. It's on.
Hello, everyone. It's an honor to be part of the UHD Master of Artificial Intelligence program. My name is Miguel Fuentes. Today I am presenting Girls Mama, a novel lightweight deep learning architecture designed to detect tuberculosis from chest x-rays. I would like to acknowledge my professor, Dr. Subhash Bhakran, for his guidance and mentorship on this research. Over the next 20 minutes, I will walk you through the global TV problem, our hybrid AI approach, and so solving the diagnostic bottleneck and the efficient results our model achieved. So what is tuberculosis? And how do you get it? Tuberculosis is caused by Mycobacterium tuberculosis bacteria. When inhaled, it settles in the lung, though it can spread to other parts of the body like the brain and spine. There are two distinct stages of tuberculosis. There is latent and inactive tuberculosis. That bacteria is basically asleep in the body. The person isn't sick or contagious, but if your immune system weakens, it turns into active tuberculosis. This is when the bacteria multiplies, destroys lung tissues, and can potentially become fatal. Active tuberculosis is strictly an airborne disease. It spreads when someone coughs, speaks, or even sings. Then germs can linger in the air for hours, especially in poorly ventilated, crowded indoor areas. Because latent tuberculosis can become active at any time, mass screening using chest x-rays is critical to catching the disease the moment it becomes active and contagious. So this chart you see over here is from the WHO, from the World Health Organization. It shows the hotspots where tuberculosis is most active. And to understand the motivation behind this, we must understand how bad it was or how bad it continues to be. In 2024, the World Health Organization reported that 10.7 million people were infected by tuberculosis, and it unfortunately claimed 1.2 million lives. While primarily targets the lung, it can spread to other parts of the body. The good news is tuberculosis is curable, and it's entirely curable if caught early. This makes mass screening critical, especially in the heavily impacted regions, like Sub-Saharan Africa, South Asia, and Southeast Asia. So, in order to access the files, I needed to get a couple certificates from the CITI program, which stands for Collaborative Institutional Training Initiative Program. It wasn't too bad. I just had to complete a couple of certificates. I had to do the conflict of interest and the human research. It was just a few modules, but it was in order to access some of the files, because I was only limited to a certain amount of the data set at first. So here's what makes it a bit hard. Here's two images. One is a healthy lung and the other is a tuberculosis lung. These images are from my data set, and it's really hard to tell from somebody untrained like myself that's not a trained radiologist which one is infected and which one isn't. And that's why we have to, before we train an eye to detect tuberculosis, we have to understand what a human radiologist is looking for. On a normal chest x-ray, healthy lungs appear mostly black because air is hollow and x-rays pass right through it. It catches the bones and the organs. And because tuberculosis requires high levels of oxygen to survive, it typically attacks the upper lobes of the lung first. When a radiologist looks at a scan, they are searching for specific white anomalies. The most distinct signs are white cavitations, which look like dark holes with thick white borders where the disease has eaten away lung tissue. So some of the white spots are what might be tuberculosis right there. They also look for consolidations, which are cloudy white patches of fluid or pleural effusion, where fluid pools at the bottom of the lung. The difficulty for human doctors is these white patches can easily be mistaken for standard pneumonia or even cancer. The bottleneck in medical imaging. The standard gold method for screening pulmonary tuberculosis is a chest x-ray. However, relying solely on human radiologists creates a bottleneck. Human analysis is dead, subjective, prone to fatigue, and time-consuming. Furthermore, tuberculosis leads to look remarkably similar to pneumonia or COVID-19, leading to misdiagnosis or further testing. More importantly, the regions hit hardest by tuberculosis have the fewest radiologists available. Artificial intelligence offers a scalable solution, acting as a tireless second opinion to triage patients rapidly. Deep learning medical imaging. Traditional machine learning requires manual feature extractions, which can take time, while deep learning automatically learns features from data. Convolutional neural networks, CNNs, are widely used because they capture spatial patterns in medical images, such as lesions and lung abnormalities. Related work in the research gap. Previous studies have successfully applied convolutional neural networks like DenseNet and ResNet to detect tuberculosis, achieving accuracy in the high 90s. My direct baseline for the study was a recent hybrid model combining Ghost Network and mobile VIT, which achieved excellent results. However, transformers are memory hungry. The baseline requires nearly 8 million parameters. That gap we identified as deployment. A clinic in a poor rural region cannot afford high-end GPUs. Our goal was to beat the baseline while drastically reducing the computational size and maintaining high accuracy among other metrics. Data collection. So the data I collected came from two data sets. One is the CXR database, which stands for Chest X-ray Database. The other is the TBX11K dataset, which stands for Tuberculosis X-ray 11,000. The CXR had 7,000 images, while the TBX11K had 1,600 images. And we used, for both the data sets, the split was 70% for training, 15% for validation, and 50% for testing to ensure strict separation between training and untrained testing data. Data pre-processing and optimization. Because this research emphasized efficiency, our pre-processing pipeline had to be highly optimized. We conducted all experiments on a consumer laptop with just 8 gigabytes of RAM to simulate real hardware limits. We converted images to grayscale, resized them from 512 by 512 pixels to 256 by 256, and normalized the pixels. The most critical step was a memory optimization technique, casting the data set to floor 16 position. This instantly cut our RAM footprint in half, allowing us to process 7,000 images seamlessly. GhostNet and cheap operations. Instead of computing every feature map with expensive convolutions, GhostNet computes a few and generates the rest, using inexpensive transformations, reducing parameters and computation, while maintaining similar performance. GhostNet solves this by generating only a small set of intrinsic feature maps, using normal convolution, then creating additional feature maps from them. Using cheap operations, such as depthwise convolution, linear transforms, or simple pixel operations. Lambda vision and state space models. To understand why our model is so much more smaller and faster in mobile UAT, we have to look at the state space models, specifically lambda vision. Traditional transformers are powerful because they look at the whole image at once. However, they use self-attention, which scales quadratically. If you double the image resolution, the memory cost quadruples. This is why the baseline model requires nearly 8 million parameters. Mamba solves this using the state space model. Try to think of a transformer like someone trying to read a book by constantly looking back at every single word they've read. While a solid state space model, on the other hand, keeps a running summary in its head. It updates its end state step by step. How GhostNet extracts textures. To understand architecture, we start with the local feature extraction, powered by GhostNet. Traditional CNNs apply heavy math to every single filter, which consumes massive amounts of RAM. As in our code, the Ghost Module 2 fixes this. First, it uses a standard convolution to generate a few core features, then it uses cheap operations, specifically depthwise convolutions, to generate the rest. Inside the module is a DFC attention, decoupled fully connected. This layer calculates an attention map and squashes it between 0 and 1 using a sigmoid activation. It pretty much try to say multiply against the features to say ignore the red buttons and focus on the cloudy lung tissue. Ghost Mamba architecture. While GhostNet looks at the local textures, the Mamba vision blocks provide the big picture. In our code, the Mamba vision blocks take the 2D feature map and plans into a one-dimensional sequence, converted into a sequence of patches. It passes these patches through the Mamba layer, a state space model using 1D convolutions. Combined with multi-head attention, this allows every patch of the lung to communicate with every other patch, making it incredibly easy for the AI to spot lung symmetry. Finally, in our TB and the traverse function, we alternate these blocks. We extract the local details, look at the global context, extract deeper local details, and look globally again. The whole thing is pulled into a 512 node dense layer with a 40% dropout to prevent overfitting. And finally, up with the 2-class softmax layer that makes the final decision of whether it's tuberculosis or normal. So here is the fiber fusion. Here is our model. We alternated between Ghost and Mamba blocks to get the best of both worlds. The Ghost blocks act as local feature extractors and progressively shrink the image resolution, which keeps the computational cost extremely low. Once the resolution is manageable, we inject the Mamba block to establish a global spatial awareness comparing the left and right lung. By interleaving them, the network continuously updates the Hello. Okay. By interleaving them, the network continuously updates its understanding of both domains. Hello. By interleaving them, the network. Okay, once the resolution is manageable, we inject the mumble block to establish global spatial awareness, comparing the left and right lung. By interleaving them, the network continuously updates its understanding of both the microscopic texture of the TB lesion and the macroscopic structure of the chest cavity, resulting in high accuracy with minimal parameters. So here's an early example of a bat model. While I was early training, pretty much the model for both the data sets, it just said yes. This one was because I trained it on a few epochs, and what's called, I learned my lesson and adjusted the learning rate. And this is just bad because it just says yes to everything. The model did not learn. So the training hyperparameters I used for what's called afterwards was I used the same parameters to ensure that it was strictly controlled and reproducible. We used TensorFlow and Keras. The model was trained using an atom optimizer with a learning rate of 0.0001 to ensure stable conversions. Binary cross entropy was used. For classification, we trained with a batch size of 8 over 13 epochs, utilizing early stoppage for patients of 5. Meaning if the model learned around epoch 8, or let's say if the model learned around epoch 7, but around epoch 11 it would have stopped, what's called learning, it would have started classifying. And early stopping for patients of 5, and the dropout layers of 40% to prevent the model from memorizing the data and overfitting. So here's when we start getting better results. And the left one is the CXR confusion matrix, and the right one is the TBX11K. The CXR had 1,050 images, and out of that it had 539 true positives, 504 true negatives, but it only had 3 false positives and 4 false negatives. And each epoch took about 53 to 60 minutes for the CXR, while on the TBX11K, each epoch took 12 to 14 minutes. And on this particular confusion matrix, it had 0 false positives and only 1 false negative. Here's the receiver operated curve for the chest X-ray on the left and the TBX11K on the right. The ROC curve further validates our results. It was near perfect for both data sets, 0.99. 0.99969 for the CXR, and for the TBX11K it was 0.99357. Both the models ran for 13 epochs. Here's the precision recall curve we had. It showed that the model just didn't blindly guess TB to get a high score to maintain incredible precision, even when pushing for maximum recall. And for both of them, the precision recall curve was over 0.99. I must address some limitations though. The images I used were all from adult chest X-rays. None of them were for pediatrics because I could not get images from children. That is more protected, and the data set was not available to me. Although I would like to include that for future work because that could be beneficial for children that develop tuberculosis. And finally, we have to acknowledge the hardware constraints required. It required me to downscale images, which might have missed obscure microscopic lesions. For future work, I would like to expand this binary model into a multi-class system that can simultaneously screen for pneumonia, COVID-19, lung cancer, and also test its efficiency of 3D CAT scans, which are a bit different because they're 3D-dimensional instead of the 2D X-rays. So this research got accepted by a conference, by an international conference on the AI Revolution Research Ethics and Society. And for future graduates here, I recommend submitting your capstones to research papers. You don't know what might happen. Worst thing they could say is no until you had improved your paper. I didn't think that would happen to me at the beginning of the semester, but it did. And I got the opportunity to go to Las Vegas, present the research among other professors, among researchers, other professors and graduate students like myself. The conference was in the Luxor Hotel. That's an image of the conference room. I presented about 2 weeks ago in Las Vegas. And let me see if I can include a small video of it. And that's pretty much the same presentation I did over here, just presented to Las Vegas. In conclusion, Bill's memo proves that we do not need massive computationally expensive models to achieve high results. but in medical imaging by fusing GhostNet's cheap local operation with MongoVision's global state space modeling. We create an AI that is highly accurate and extremely lightweight. Thank you for your time and attention. It has been an honor and privilege to be a UHD master's student. I'm now open to any questions you may have.
First name is Stephen. And I believe we have time for questions.
Were the images in the data set produced with like similar equipment and settings, so they were like pretty standard? And if so, like, is that gonna have an impact on, you know, you wanna look like a big global context, if there's like different equipment used, is the pre-processing enough to like, you know, make sure that those results are applicable to images captured in different equipment settings?
That is a good question, and the images were from two different data sets, and one of the data sets I know used images from the Shenzhen and Montgomery, from two different parts of the world. The other images, it does not tell me where they came from, but that is something that you, Scott, that I did notice that some of the images were not exactly like the same. Like it matters where somebody's like standing, like if somebody's like a foot away from an x-ray, or a few inches, it changes a bit like how it's done. And yeah, I think that could have affected it a bit, but how I downscaled it from 512 to 256 affected that as well.
Any other questions for our speaker? It's you mentioned, there's of course it's good natural stuff is can you replicate this for other lung anomalies, right?
Yes.
Is there data out there that would be accessible?
Oh, actually, one of the data sets that I gathered from the chest x-ray included thousands of images from pneumonia, and from pneumonia x-rays, and from COVID-19 x-rays. It just, if I would have had more time, it's something I would like to test in the future. Because it had like 7,000 of each image.